All right, so we got the torques. Now we're going to set them equal to each other. So we're going to minus L K Q Q over 2h squared is equal to mg L over 2 minus mgx. We're trying to find x actually, so maybe we shouldn't do this. Maybe we should keep it factored. mg L over 2 minus x. Okay, so we're going to get okay, so let's just do a solve. Command and tech if I'm right. Solve minus L K Q Q. Oh wait. I want to fix this actually. Q2. I want to make a different Q. Okay, that stays the same. That just expands out. Divided by 2h squared mg. Oh wait, I did this wrong. 2h squared equal to mg L over 2 minus x. Is that right? That looks right to me. So let's just plug it into ChatGPT and see what's good. Oh wait, I did the wrong problem. Hold on. Stop it. Okay, wait, we need to do this problem. Okay, wait, let's do this problem now. All right, so problem 4. Find the position x of the mass m such that the system is horizontal and balanced. Okay, so let's draw the pivot thing again. This. So it's length L. This is X. This is Q1. This is Q2, Q3, and Q4. Okay. Distance H. The mass M. Gravity. Then our coordinate frame plus X plus Y minus Z. So that means that okay, we set up our coordinate frame. We got all of the parts of the thing. This is at L over 2. Origin. So this is O. Okay, so now we've set up the whole problem. Good. Now we just need, actually we have it. So now we need to say Q1 is equal to, let's say, it's plus Q and then its position is minus L over 2, 0, 0. Q2 is equal to the charge plus 2Q L over 2, 0, 0. Q3 is a different thing plus big Q, and it's L over 2 minus H 0. And then Q4 is equal to, again, plus big Q minus L over H over 2 minus H 0. Okay, so let me write that down in here. So now we're going to do problem 4. Okay, so we're going to have Q1 it's going to be equal to charge. This is just going to be Q, and then it's a list minus L over 2, 0, 0. Okay, now I'm going to just copy this. And actually, oh wait, you know what I want to do? I want to do this. Wait, how do I do it on the same? I think that was what I wanted. Yeah. All right, so this is going to be 2, 2, 3, 4. And then we're going to have this be 2Q L over 2. And this is going to be big Q L over 2 minus H. Then this is going to be big Q minus L over 2 minus H. Okay, we have all of our charges now. And then what we want to do is I mean, really, it's just going to be pos Q. It's just going to be cross the pos of Q times, well, a force. So let's not pattern this. Let's just say Q1. So it's the position of Q1, and it's the force of Q2 on Q1. So this is the well, that's not right at all. That's definitely wrong. Because there should be a non-zero torque there. Oh, wait, actually, that is going to be a zero torque. Oh, that's cool. Okay, but we wanted this one. Okay, so this is T1. Then T2 is going to be equal to the cross of the position of Q2 and the force of Q. Wait, no. Hold on. This is totally wrong. That's why that looks wrong. This is the charge of Q4 on Q1. That's the torque. That looks way more reasonable. Okay, that's the first torque. This is going to be the torque from Q3 on to Q2. That's the second torque. Okay. But okay, so okay, so first we need the forces on the rod. The forces on the rod are going to be the gravity causing tension. So Ft Fe1 or let's just say FEL, left coulomb, FER, right coulomb, and then FN, pivot normal. And why did we get to say that the pivot force was 0 last time? Oh, because it's not that the pivot force may not be normal, or the normal force might not be 0, but the torque is 0 because we take the origin to be the reference point. Okay, so we're gonna get torque normal plus torque EL plus torque ER plus torque tension. Okay, so the since we take torque equal to R plus F, where R is reference to be pivot origin, then R is 0 and okay, so this is 0. All right, so we now showed the normal torque. The torque due to the normal force is 0. Now we need E right and E left. Okay, so first we want to compute all the R's. Okay, so R T is going to be equal to so this is going to be basically from origin to point where tension force acts. Okay, and that point is going to be just you know x minus L over 2 0 0, minus the origin, which is just deal with the heat. Okay, so we have the okay, so now we're going to need we're going to need the norm of it. So the norm of RT is going to be equal to just x minus L over 2. Okay. Okay, so that's the position to the tension force. Now the position to the let's say the left electric force is going to be equal to, and I'm just going to write these out because they're so basic. This is going to be minus L over 2 0 0 with norm L over 2. Okay, now the position to the right is going to be just L over 2, 0, 0, with norm L over 2. So, okay, so we have all of the positions. Now we need the forces. Okay, so now we need the tension force. We have a F equals MA problem. So we have, the dot mg, this, and then we have ft. Ft is equal to, this is going to be plus y, is equal to ft plus mg is equal to 0. So ft equals minus mg. Now that's confusing, actually. Yeah, I guess that's right. The tension force is minus mg. Okay, so we figured out that the tension force is that. Now we need the left electric force, so FEL. This is going to be equal to KQ um, so it's going to be KQ big Q divided by H squared times 0, 1, 0. Okay, FER. This is going to be basically the same thing, except it's 2K Q big Q over H squared times 0, 1, 0. It's the same. Same logic. Okay. Now we just have to compute the torques. So torque due to the tension is going to be equal to, let's see, x minus L over 2, 0, 0 cross this should be equal to because the G. Okay, wait, hold on. Let's just ask this question really quick. If I have a physics problem where I define the coordinate system so that x plus x to the right plus y up and into the page is minus z, then what is the direction of the gravity vector? Is it I think it should be 0 minus 1 0 because then minus mg. What is the direction of the gravity vector? Is it 0 minus 1 0? Okay, so g is 0 minus 1 0. And g is equal to 0 minus g 0. But that says that the tension force is pulling up. Dude, I actually love these physics problems now. Now that I started doing them, they're so fun. And we get like, there's like 8 more left to do. Physics. Bro, why is it that physics, why is it that the physics students are the cringiest of all, bro? You think about it right way, the rod doesn't feel mg directly. It feels the tension from the string at the attachment point. So the sum on Fy is equals 0. So T minus mg equals 0. So T is equal to mg. The string pulls up on the mass. So the mass pulls down on the rod with equal magnitude. So the force on the attachment point sense so the rod feels minus tension. Wait, Ft equals 0 T0 because it's pointing up. Okay, but then FG, I don't like the T and W. I like the F's because F, the notation tells you that it's a force. FG is going to be equal to 0 minus mg0. Okay, that's good. That makes sense to me. So now we know that ft plus fg is equal to 0, thus t equals mg. Okay? But I really don't understand the tension forces. Okay. By Newton's third law, um, the Ft, yeah, bro. You got to think about forces from something to something. The force on the string due to the mass, the force on the string due to the mass So we have the force from the string, from the mass on to the string. That's the forces N by N on the mass. Forces on the mass, string on mass, and gravity on mass. Okay, fine. I think I get it. Kind of. I mean, I'm not in a mechanics class, so we don't really have time to keep doing that. Okay, so let's so we have okay, so let's do this. So the force due to the tension is going to be equal to 0 minus mg 0. The force of the let's just say, let's just do it as normal electric charges. It's going to be Q4 on Q1 is going to be equal to minus K, why am I fucking on autopilot? What are the forces? The force is going to be um K Q big Q over H squared, then times the norm of the displacement vector from Q4 to Q1. That's straight up 0, 1, 0. Okay. Now we have F from Q3 to Q2. Okay. Remember, the system is the rod. So this is going to be equal to 2K Q big Q over H squared. And then what's the displacement, the normalized displacement vector? It's still 0, 1, 0. Okay. Now let's get the torques. So let's do torque due to the tension. This is going to be equal to, oh wait, let me write down the R's. So RT is equal to x minus L over 2, 0, 0. R let's just say EL. RL is going to be minus L over 2, 0, 0. And then R is going to be just the opposite. L over 2, 0, 0. All right, let's take some freaking cross products, bro. Okay, so now torque due to tension is going to be equal to RT cross FT. So this is going to be x minus L over 2, 0, 0, cross 0 minus mg, 0. Now let's just think for a second. What is the force? So it's going from our origin, we're going this way, and then we're going down. That's a negative torque. Okay, and perpendicular, so we can just do, so this is going to be equal to, so if it's a negative torque, well, I guess the norms, right, because this norm, then that norm. So the norm, let's just do it by the norms. So we're going to get x minus L over 2 times mg times 1 times 0 minus 1, 0. There we go. That's the right way to do it. Do the norms. Or wait, no. 0, 0 minus 1, because it's in the z direction. All right, so now we can scalarize. So we can get just minus mg times x minus L over 2. Bro, I really like the cross product. Who made the cross product, man? Smart person. Pretty interesting. And I haven't even done the determinant one. I just did the freaking the lame one. Where's history? Names and origin. Willard Gibbs. Oh, this Gibbs? Really, dude? Like Gibbs free energy? Oh, look at that list, bro. You know, I didn't know anything about Gibbs, but holy shit, this guy ruled. No way, dude. His thesis was on gears? That's fucking cool, dude. They still have this thing? Oh, what a whacked up thing. It's dumb. Let's see, what does that link actually go to? It's so annoying. Alright, anyways, that's crazy. Gibbs, bro. Alright, enough of that. So let's keep chugging along here. So now we have one of the torques. Let's get the torque due to the left one is equal to R L cross R F of Q4 to Q1. All right, so this is going to be equal to minus L over 2, 0, 0, cross 0 k q over h squared, 0. Okay, so perpendicular. And then the sine, let's do the sine. We're going boop, boop, boop. It's a negative torque. Negative torque, bro? Who the hell said negative torque? It is negative torque. I am all about the negative torque. Okay. All right, so let's just do the product. So we have the norm. All right, so okay, so we got the minus here. So this is just going to be L over 2 times KQQ over H squared times 1 times 0, 0 minus 1, which is equal to, minus LKQ big Q over 2H squared. Scale. This is the torque. This is the torque due to the left charge. Now, finally, let's get the torque due to the right charge. This one should be easier now because we've kind of done it. So R cross R F from Q3 to Q2. This is going to be equal to L over 2, 0, 0 cross. This is going to be 0, 2Q big Q over H squared with a K. I forgot the K. 0. Okay, so we have perpendicularity and we have a positive torque. So that means that we're going to get L over 2 times 2KQQ over H squared times 1 times 0, 0, 1, which is equal to LKQQ over H squared is equal to T. All right, we have our equations. Now we get to sum them up and set them equal to 0. So we're going to get torque due to the right plus torque due to the left plus torque due to tension is equal to 0. This is we're going to get minus, or we're going to get L K Q Q over H squared minus L K Q Q over 2H squared plus it turns into a minus mg times x minus L over 2 is equal to 0. So this becomes just LKQQ over 2H squared is equal to mg x minus L over 2. Okay, this turns into LKQQ over 2H squared mg plus L over 2. All right, I think I did it. That problem's a doozy to do, with the vectors, but it's way easier to think about the vectors than it is to try to, not deal with the vectors. That's kind of, I think that's the general point in physics, is everyone uses vectors because it actually is worth the time. All right. I got x is equal to LKQQ over 2H2 mg plus L over 2. I could factor out an L. Physics. 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 Okay, wait, let's go to first exam archives. Just like, I just kind of want to do all of these, bro. I don't even want to look at the, I don't even want to look at the anything. I just want to do it. What does this mean? The problem is this is some E field thing. Yeah, all these are E fields. Dude, I'm gonna have to practice so much calc. These seem insane. Oh, this one looks good. I think I can do this one. Find the net torque as a vector quantity in the coordinate system provided. I'm guessing that's an I and that's a J, and K is out. That's the way I like it. That's definitely the way I like it. Um Find the net torque as a vector quantity in the coordinate system provided on the dipole in the uniform electric. Fuck, bro. Calculus somewhere, right? Wait, where did I miss squares? What? Wait, what did I do wrong? Okay, actually, we need to do this. I need to figure this out. How it is. Oh, okay. I get what this means now, I think. But what? Sometimes it just reads my stuff wrong because of tokenization or something. All right, so that's what I got. All right, let's do that problem one more time. This time on the iPad. All right. Okay, so we have a rod here, like this. Okay, length L, H, H. I have the E here, right? Okay, good. Let's just zoom in a little bit more. Okay, we have length L. Then we have a this distance is X. This is a M. This is G. Okay, so we have gravity force. Okay, then we have, let's just say Q1, Q4, Q2, Q3. Okay, now let's just write the charges. Q1 is equal to Q minus L over 2, 0, 0. This is the full vector thing, you know, and you need 3 vectors because you got torque. Okay, Q2 is equal to 2Q L over 2, 0, 0. Q3 is equal to Q L over 2 minus H, 0. And Q4 is equal to Q as well, but this one's going to be, what the hell? Minus L over 2 minus H, 0. All right, so we have kind of the like setup of the problem. And then M1 is equal to M, and then let's just write this all out. So this is going to be X minus L over 2, 0, 0. All right. Now that we've set up the problem, Is it possible to zoom it out like less than? Oh, it does it so much. Can I just? Whoa, 100% is crazy. All right, fine. Let's do 100%. Let's get really in here. All right, so what do we need to do? First, consider it's a torque is equal to alpha problem since the let's read the problem again. Since the system is horizontal and balanced. All right, what about this? Why don't we start with just the forces? Okay. Okay. Torque equals I alpha. So, what are the forces acting on the rod? We're gonna have a rod here. We're gonna have a force here. It's gonna be F L equal to, so wait, we'll just write FL there. Then we're gonna have normal force Fn. Then we're gonna have okay, so first we have a mass, right? This mass you have to consider this carefully. So so the force of gravity is pulling it down. This is going to be equal to basically oh, and you know what we didn't do, which we needed to do. So let me zoom out. We need to write this. Plus x plus y minus z. So this is minus. This is the thing going out of the page. Okay, we can zoom back in. So let's consider this carefully. So the force of gravity is going to be m times g, which is equal to m times 0 minus g 0. Now we're going to have Ft. Ft is equal to, you know, no. Oh, that was close call. That's not right. Look, this mass is not moving. So Ft plus Fg is equal to 0. What does that mean? That means that Ft plus Mg is equal to 0. So Ft is equal to minus Mg. So we solve for the tension force, but this is not, this is Ft, let's call it M, due to the mass, not the net force, because this is equal to 0 mg 0, which is in the positive direction, on the rod, which is minus Ftm equal to Fg equal to, this is the force. Okay, so this is Ft. This is the real one. This is the one that we care about. Okay, so we finished the first force. Dude, I don't know how people do this so quickly, because like all the derivations that you need to show takes so long. All right, second. Okay, now we need this force. And this is going to be this way too. This is Fr. Okay, so Fl is equal to F of Q4 on Q1, and Fr is equal to F of 3 on 2. All right, so we have our forces. Oh, and then the normal force. Why is the normal force 0? The normal force is not 0. The normal force is not 0. Oh, and one thing that we forgot too is we need to set this equal to the origin. So first let's compute these forces, right? So let's just get these down. So so FL is equal to KQ4, which is just big Q, Q over H squared 0, 1, 0. FR is equal to 2K QQ over H squared. Okay. So we have the forces. Now let's get the R's, right? So okay, we can actually do this now. We can now say that the torque due to the normal force plus the torque due to the left force plus the torque due to the right force plus the torque due to the tension force is equal to 0. This is 0 by given. It's given that it's balanced. And it stays horizontal, therefore it's not accelerating. You know, it's not changing in velocity or anything like that. So it's 0 acceleration. Therefore, the net external torque has to be 0. Okay, now we take the reference point to be origin, which is the pivot. Hello. All right. So we take the reference point to be the origin, which is the pivot. So if that's the case, then tau n is equal to Rn cross Fn. But the normal force is applied at the reference point pivot. So tau n 0. Okay, so we can cross this one out. Now we have torque L plus torque R plus torque T is equal to 0. So what do we do? First we get R L. So this is the so let's just do this. Actually, yeah, this is actually not the worst idea. You do RL cross FL plus RR cross FR plus RT plus FT. 0. Okay, so now we kind of know what we need to find out. We have the forces, now we just need the R's. Okay, so what is RL? Let's do it over here. Let's zoom in. Okay, so RL, for instance, is going to be the O2 where left Coulomb applied. So this is going to be, minus L over 2, 0, 0, minus 0, 0, 0, which is equal to minus L over 2, 0, 0. Okay, R the tension force, this is going to be X minus L over 2, 0, 0. Okay, so now we have all the things. Now we should just be able to do, plug and chug. So first off, tau L is going to be equal to minus L over 2, 0, 0, cross the force, which is going to be 0 kq big Q over h squared. I think that's it. Okay, now we need to figure out the sign. So first off, perpendicular, and also, so we're going this way and we're going up. So this is a negative torque. So this is going to be L over 2 times KQQ over h squared times 1, because this is the sine theta, times, you've reached the maximum number of shapes allowed on a page. Delete some shapes. What the hell? Guys, this is as big as TL draw gets. It's annoying. All right, let's just make a new one. In Chicago winter, butterfly, Bankai, all right. Okay, so what did we have? We had tau L plus tau R plus tau tension is equal to 0. Ba ba ba. Now, we were computing the tau L equal to, and this was going to be like minus L200 cross 0k QQ over h squared. This is going to be, so this is perpendicular and it's out of the page, or it's into the page. It's negative torque because you go vroom, vroom. Okay, so the norm, so this norm is, so you're just going to L over 2 times KQQ over h squared times 1 times sine times 0 minus 1. Okay, so we're going to get, so now I'm going to say scalarize, because we're going to do we're just going to get rid of that thing, because I guess we're allowed to. It's a little bit sus actually, but it's fine. So we're going to get minus L KQQ over 2h squared is equal to the torque and no harpoon of the left. Okay. Now let's do torque on the right. So this is going to be equal to RR cross FR. So this is going to be L over 200 cross 0 2k k q q over h squared 0 this. I've done this so many times at this point. It's actually too memorized. You know, I wish I had forgotten some of this, but and then what's the vector? Positive. Actually, did I mess something up? No. Okay. Butterfly. Bankai. Okay, so now we have torque on the tension. Now this one's interesting. There's still R tension cross F tension. So this one's kind of interesting. So we're gonna get x minus L over 2 0 0 cross. Now the force we determined was 0 minus mg 0. So the torque is negative. So first off, they're perpendicular and negative. So we're gonna get okay. So now we have basically LKQQ over h squared minus LKQQ over 2h squared plus, ooh, I think last time there was yeah, I have a minus there. The force is negative. It's 0 minus mg 0. This torque is negative. Oh, because I didn't norm it. That's why. I didn't norm it. Look, you need to, implicitly in here, you need to take the norm of this. Norm. I should just get in the habit of that. Damn, that's crazy. That could bite you in the ass for sure, dude. That's not good. Okay, I got it. Okay, so then this is going to be minus mgx minus L over 2 is equal to 0. Okay, now we can actually do this fun thing here, I think. Right? Can't we just do like 2 over 2, and then we get 2 LK Q Q squared minus LK Q Q. This is going to be equal to so that's the distance from the side so that it's all balanced. I'm going to get a LaCroix. That was a good one. That was a good problem. I'll probably try to do that one more time tonight, but I think the only real hiccup I have is I mean it all conceptually I think makes sense. R cross F. I think maybe I could be more explicit about the definition of the R cross F thing. Like tau so instead of the determinant thing, we're doing norm of R, norm of F, sine theta Oh, I guess, it would be good to do a problem where, sine theta is not 1. And then this is going to be n hat, which is the, what is this? What is this thing? What is that? That's called unit vector perpendicular. Yeah, we should do a problem where, cause like let's say you have two vectors. How do you compute the angle between them? What's the easiest way to compute the angle between them? No, without a calculator. No calculator. He probably won't give us that. Oh, really? You can do that? Yeah, that makes sense. But I need sine. But to compute the cross product, I need the sine, dude. What the hell? Okay, if that's the case, then we definitely are not going to need this. All right, he definitely won't have us do that then. That would be insane, man. Or the angle is given though. Hmm. All right, so should we do the last problem then? All right, so these two, 5 and 6, they're E field problems, so we're kind of good on that. This is not going to be a torque problem. All right, I'm gonna get LaCroix. All right. Three positive charges, Q1, Q2, and Q3, are connected by two strings of equal length L. Due to mutual Coulomb repulsion, the charges spread out and form a straight line such that the distance between 1 and 3 is 2L, and with 2 in the middle. Okay, yeah, all right. Find the tension force in each string. Bro, this one sucks. I really hope I don't get this one. I don't like this one, man. All right, so let's box this. Okay, so let's do this. Problem 7. All right, so we're gonna have okay, so first take the system to Q1, Q2, Q3 plus 2 strings. Then no external forces. So COM sys has then the system, unless rotating, also has 0 exit. So for all bodies, a body. All right, so we got that. So now, what do we want to do? We now prove that we're in equilibrium. Thus, equilibrium. Okay. Let's take the system equal to Q1. Then we're gonna have F equals MA problem. All right, so we're gonna have, what are the forces? We're gonna have force of tension plus force 3 on 1 plus force 2 on 1. Proof. Okay. So first off, let's just do this thing. So we get K, Q, oh yeah, I forgot to do one more thing. We need to define the charges, because I don't like just leaving this here. So I'm gonna actually say Q1 is equal to, Q see, they can't be the same name, so I need a all right, well, I think we can do that. So it's gonna be Q1 minus L, and we can just leave it like this because it's in a line. Then Q2 is equal to another magnitude Q2, 0. So this is the origin. And then Q3 is equal to Q3 L. Okay, good. Now we want to bring this over here, and we want to say that the F due to 3, let's just do 2 on 1, going to be equal to KQQ over L squared times minus 1. F3 on 1 be like K Q Q over 2L squared minus 1. Okay, so then we're going to get F2 on 1 plus F3 on 1 is equal to minus KQQ over L squared minus KQQ over 4L squared. Okay, so we got that. So that must be the tension force, right? So then Ft plus minus 5KQ over 4L squared equals 0. Ft is equal to so the norm of that, right? But this vector is going to be times a 1. So then t is equal to 5. Is that it? Now we just got, this is t1. Now let's look at the t2. Okay, so t2. Whoa. Oh, you can do a rectangle select. Okay, that's good to know. All right, so we have T2 F equals MA, cis equals Q3, F1 on 3 plus F2 on 3 plus F tension is equal to 0. So this is going to be, let's just do it, like K Q Q over 4L squared plus KQQ over L squared. Because this is a 1. This is a 1. So then we're going to get the... Oh, but you know what I didn't do? I messed this up from the beginning. Because this needs to be... No. Fuck. Okay, because this force... Alright, let's go back. Let's just delete all this, because this is no good. I messed this all up. Okay, so the force of 2 on 1 is going to be equal to K times Q1, Q2 over all right. So we have k q1 q2 over L squared. Then we add k. So now the force of 3 on 1 is going to be k q1 q3 over 2L squared. Okay, now we're on to something. But the thing is, this is a -1 in here, and this is a -1 in here. So I guess we just have to leave it like that because the charges aren't equal. Well, we can at least do this. 1 Q2 over okay, this is 4L squared. So here we can make it 4 k q1 q2 plus k q1 q3 over 4L squared minus. So this has got to be. So this is so then this is plus ft is equal to 0. So then ft1, and this is still a 1 direction, but we can scalarize it. So that this is going to be so t1 I think that is closer to what we should be expecting. Butterfly, Bankai. All right, so let's do the second one. All right, so let's ignore all that. All right, so the force of 1 on 3 is going to be equal to k q1 q3 over 2L squared, and then f of 2 on 3 is going to be equal to, and this is times a 1. Come on, you cannot forget this shit. K q2 q3 over, what is the norm of the vector between this? It's L times 1 as the unit vector pointing in that direction. Okay, so now we can just add these. So we're going to get k q1 q3 over 4L squared plus k q2 q3 over, and we're scalar. Let's just say we're scalarizing now. Over L squared plus ft2 no hat is equal to 0. So then we're going to get the same thing, right? We're going to get k q1 q3 plus 4k q2 q3 all over at 4L squared. This is a minus is equal to ft, but 2, but so the tension Ft, the tension T2 is equal to just something like that. Oh yeah, one thing. Oh yeah, I said the system. Yeah, I said the system. Okay. Wait, what? T12 is equal to let the string tensions be T12 and T23, all forces alone. Look at charge Q1. It is repelled leftward by um ooh, yeah, you can factor out the K and the, but this is it. K Q1 Q2 over L squared plus K Q1 Q3. So that's that. All right, so I mean, I feel like that problem is actually pretty easy. 7 is not so bad. Okay. Were there any static point charge torque problems on here? Where was it? Let's see, are any of these torque problems? These are all electric fields except for, I think there was one. No, electric field, E field, electric field. Oh, I think it was this one. This one I spent a little bit trying to understand. It's so weird. Mainly because like you need to remember this is the force and you're balancing it with I mean, because like the derivation is pretty nasty, so you need to just remember that for something to orbit, the what is it? The Let me get it right. What does the velocity need to be for something to orbit in a circle? Oh, the okay, the centripetal acceleration. Okay, cool. V squared over R. So that's what he did. Is he said that uh, the force is this KQ1 Q2 over R squared. But then he's saying this is equal to mv squared over R. Oh, because this is the centripetal acceleration. I get it. I don't think I could do this problem myself, but um yeah, all of these have this charge density thing. Uniform infinite line of charge. No, yeah, electric field. I mean, we haven't talked about charge being able to be anything but a point charge. There's no way that this is on there. Oh wow. So you need to compute the torque at wow, that seems crazy. Whoa. We're gonna be able to do that? That's actually crazy. Why did it give me okay, well, uh two fixed charges. Charge at the end of a string near a fixed. Let's look at the torque problems. How can we modify this one? I wish there were more problems. There aren't that many problems that apply to us. Do you see this lambdas? When the lambdas here, we're not there yet. Charge density, finding V, two spheres, find something. So really the statics problems barely come in. Alright, it's time to, I'll probably come back to some of the problems at the end of the... There you go with electric fields. Okay.